So let's go over the periodic 1 worksheet. Okay, so this is a really good review for our quiz. Okay, so what we have here in this question, we have outer layers of the sun contain helium atoms in various excited states. Now you should know that an excited state would mean that electrons are in higher energy levels than they are normally. You know, the Aufbau principle states electrons always go into the most stable low energy state. Any case, we've got a helium atom. We know that helium has 2 protons and 2 electrons. And we're saying that 1, okay, is in the 1s orbital, okay? So the 1s orbital is a very small orbital that surrounds a nucleus. That's the 1s. And then we're going to say that we have what? Let's make this a 3p. Now we know that the n number, the quantum number, principal energy level index is size. So 3p is going to be a much bigger orbital, okay, than the 1s. So we've got some electron density that it definitely exists outside the 1s. Okay, this being 3p. So what we're going to say here is that we have an electron in the 1s region, and then we have one in the 3p orbital. Okay, and what we can say, and again the question is based on the effectiveness of screening, estimate the ionization energy of the 3p electron. Okay, so how much energy does it take to remove this electron? Well, we do know that screening is more effective between energy levels. So this is n equals 3, this is n equals 1. And remember, it's all about size. So the n equals 1 is the smallest orbital, and this kind of encapsulates the protons. So P being so far away and this electron being so close, we can assume almost complete screening in this case. And how can I say that? Well, I can say that because anytime I've got electrons so close to the nucleus, it's going to make it tough for this electron to feel that. So the effective nuclear charge of this decreases. So any case, that being said, and assuming the screening is going to be as complete as it possibly can, being this one electron, this very small orbital, how do we measure the energy? Well, if we remember, we measured energy levels with the hydrogen atom using the Balmer equation, okay? And it was an inverse square law. And so we're going to have to use that. Now we can, even though it's not hydrogen, we could use it because assuming complete screening, it's a 1 proton system. We're going to assume that this electron takes away 1 proton. So therefore it's kind of like 1 electron feeling what? 1 proton, and that is just like hydrogen. So let's go to our reference table for that equation for a 1 proton, 1 electron energy level. So here's our equation right here that we're going to use to measure this. Again, this is for a hydrogen atom. This is what Bohr used to measure the individual energy levels. So let's do that. So I've written it here, and this is the actual energy it takes to pull an electron from the first energy shell of hydrogen, which is a 1 proton, 1 electron system. And it's n squared, and since we're talking about pulling electrons from the 3p, or n equals 3, we're going to divide by 9. Okay, and when you do that, you get approximately 2.4 times 10 to the negative 19. That's a 19 joules. Okay, and that would be the energy to pull an electron away. Again, the only way to do this was to, again, assume that I'm dealing with what? I'm dealing with a 1 proton, 1 electron system. All right, and we're dealing with almost complete screening like we did and talked about here, okay, in this worksheet that we did in class. So that's approximately the answer there. All right, so let's move on to the next question. Okay, in 7.13, crazy numbers here, we want to redraw the diagram that includes lithium plus 2. Now, I do apologize, my drawing here is a little different than the diagram posted, okay, in the key or the actual worksheet, but let's just work with what we have here. In the diagram, we have helium plus, we have hydrogen, and now they're going to ask for lithium plus 2. Now, very important you recognize what we have here. This is called an isoelectric series. Now, what's so special about an isoelectric series is they have the same number of what? Same number of electrons, yet different protons. Helium has 2 protons, 2p. Hydrogen has 1 proton. Lithium has 3 protons. Okay, helium has 1 electron. It lost 1, so that's why it's plus 1. Helium just had 1 electron. It's neutral atom. And this one lost 2, so it normally had 3 protons. So they all have the same number of electrons. And that's where we get the isoelectric series. Now, what dominates an isoelectric series is the Z. Z is important. Since they all have the same number of electrons, there's no real difference in their interactions. What dominates is how many protons you have. So with the same number of electrons, how well does this electron feel the proton? Well, a lot more. How can we evaluate that? Well, the Z squared rule is in effect in an isoelectric series. So to understand this, if I'm going to draw an energy diagram for lithium plus 2 and see where it exists, what I'm going to do is I'm going to take the idea that I have 3 squared compared to hydrogen. When I do my Z squared rule and put the protons, what I get is 9. And what this means, party people, is that the electron feels the nucleus 9 times when you have 3 times the number of protons, or in this case you have 3. So we're going to say that lithium plus 2 is going to be 9 times more stable in each of its energy levels. So if I wanted to redraw them as the key shows you, what I would do is I would use, because again it's a 1 electron system, what I could do is I could take this equation for the first energy level, 2.8 times 10 to the negative 18, and divide by 1 squared, and take that value, and you're right, times that by 9, and that would equal the energy of the first energy level, which would be way below the rest of these. Why? It's got more electrons, more protons, so it's going to be a lot more stable. So the energy level of that orbital is going to be much lower. Lower energy means more stable, so it's down here. And I can do this for the next energy level. I can take the 2.18 times 10 to the negative 18. I can do this. Divide it by 2 squared. That's that Balmer equation. And yes, times that by what? 9 to get the energy for the second energy level. Each of the energy levels, n equals 1, 2, and 3, are going to be 9 times more stable and be lower this way. And I can take the one we just did for 3 and times this by 9 and find that on the graph. Bottom line is isoelectric series, it's all about the protons. And the greater the protons, the more the electrons are going to be pulled in closer, or the orbitals will be pulled in closer, and therefore they're more stable, harder to remove, takes more energy, or they lose a lot more energy, either way. So it's important you understand that, not exactly figuring out the information, or you don't have to kind of put that in there. All right, moving forward. 7.2, what's the atomic number of an element that would occupy position row, column 7 of the periodic table? That's pretty simple stuff. So looking on our periodic table here, we can see that we are in row 7, n equals 7, and then 17, and atomic number is 117 there. Tough one. So valence electrons for the next one. Valence electrons, are these electrons that could be easily removed. They have lower ionization energy. Remember that we actually found valence electrons. These electrons are available for bonding. They're the most unstable, so they exist in orbitals that are proximity based a little farther away than the core electrons. So we need to know what electrons are in unfilled energy levels that are the farthest away. So let's go through this. Carbon. Here's my carbon. Carbon is 1s2, 2s2, 2p2. So there'd be 4 electrons that could be easily removed before I move the core electrons. Core electrons, electrons in a filled energy level. Okay, so they would have 1, 2, 3, 4 valence electrons outside a filled energy level. So 4. Okay, bromine. Now bromide's a little more confusing. You got 4s2, 3d10, okay, 4p1, 2, 3, 4, 5. So in the fourth energy shell, there are 5 p's and then 4 and 2 of the s's, and we would say that there are 7 electrons beyond, okay, this filled d level here. So we would say bromide, like all elements halogen-wise, have 7 valence electrons, 5 from the p and 2 from the s. So 7. Chromium, transitional element. All right, transitional elements, okay, with between 3 here and 11, okay, unfilled d orbitals, they are a little different. They get their valence electrons from 2 different energy levels because the S and the D are very, very similar in energy level. Of course, the S is lower and then eventually becomes higher as we have divergence. But, so chromium, generally speaking, its valence electrons are the electrons that it can react with. In the case of metals, metals lose electrons to react. So if I get up close and personal with chromium, okay, I can see that chromium can become +2, +3, or +6. So we would say chromium can have 2 valence, 3 valence, or 6. And it loses electrons from the D and the S, especially if it's +6. Well, all of these lose from the S first, as we've talked about. So the transitional elements are unique in that they lose electrons from 2 different energy levels, unlike the ones we just talked about. But again, their valence depends upon what oxidation states they become. So we would say 2, 3, and 6. 2, 3, and it's an and sign, and 6 are possible. All right, go get tantalum. So tantalum is located here under vanadium, niobium. So we have what? 6s2, these are definitely lost, and we can lose 1, 2, 3. All right, and of course tantalum, just like these guys, can be +5. They can lose all 3. Now, never going to ever have you know that, okay? But given the idea, you should know that these guys can lose what? Their S first and then some D. They can lose from the 3 and the 4s, 2 different energy levels. Given this information, you should be able to look it up and say, hey, it's +5. You would need the periodic table. So it has 5 valence. 3 Ds get lost. Okay, 3 of the 5D and 2 from the 6s. So 5 for this guy. Zinc, let's go look. Zinc is an interesting case because you would think it has no valence since it's an element that what? Filled its third principal energy level, right, by filling the 3d10, but it has this 4s2 that it loses. So it has 2 valence. Notice it becomes +2 because it loses 2, and the 2 it loses the 4s, so 2 valence. So 2 it is. This, of course, is 5, and this is 2. All right, platinum, a noble metal. Let's go get it. So platinum is located down here, and it can lose 2, which, of course, is from the S, and it can lose 2 more and be +4. So 2 and 4 are its oxidation numbers, and therefore those are its valence electrons. So platinum can have 2 valence and or 4. So again, the ones that have multiples have multiple oxidation states. Okay, transitional metals are famous for having multiple valence electrons as well. Okay, next one, 7.4. Determine the energy level diagram in shorthand notation for electron configuration of the fluorine atom. All right, so the fluorine atom. So fluorine is 1s2, 2s2, 2p5. As you've learned, this is an unfilled energy level. It's the valence shell. Now they want to draw an energy diagram in a shorthand notation. So the shorthand notation would mean you would take the nearest or closest noble gas. Helium is 1s2. So we would take helium, as the 1s2, then write 2s2, 2p5. So this is the longhand notation, it's the shorthand. I'm not sure how much you save here by writing HE, but that's what I ask you to do. Now they want an energy level diagram. Well, the 1s2 is going to be the lowest energy. All right, so here's an energy diagram, here's energy. The lowest energy orbital would be the 1s2 box. Okay, the next highest energy level would be the 2s2 box. And the next one would be, changing inks because I can, is the 2p. Now, of course, p has a total of 6 electrons. Its M sub L number is -1, 0, +1, so there's 3 of them. And if I'm going to do this correctly, the 1s2 would be filled, and I would pair up the spins so they cancel each other. And then, of course, using Hud's rule, I would go in. Number fluorine has 5, so we do all of that, and then we have that right there. So there's your energy diagram with orbital, shorthand notation. Fantastic. Moving on to 7.5. Determine the configuration of indium, first in shorthand and then in full form. Let's go. So indium, I'm going to go right here. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. This would be 4d10 right here to cadmium, sorry. And this is going to be what? 5p1. Now, that'd be the longhand. The short notation would be up to krypton. It's the closest or most recent noble gas, so it'll be the krypton, and then you'd have this 5s2, 4d10, 5p1. Okay, let's go there. Again, the periodic table makes life easy. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, back to 3d10, 4p6, 5s2, 4d10, and then 5p1, longhand. However, as we just said, all of this to 4p6 is krypton, so Kr, and then 5s2, 4d10, 5p1. Good times. So in this next question, we're going to write a ground state configuration, electron configuration of electrons going in order from lower energy to high energy. Aufbau principle is in effect. And an orbital diagram for chromium +3, an ion. So let's go to the periodic table. So looking at chromium, it's 4s2, 3d4, and having that information, now let's go back to the paper and write that out. All right, so chromium, a atom, neutral, shorthand notation would be argon, and you would have 4s2, 3d4. Now, in truth, this isn't correct, right? This really should be argon. We should know better now that one of these electrons will fill the D in this case, 4s1, 3d5. But that's for chromium. They want chromium +3. Now, let's write out the boxes for these guys. And I don't have to write, I'm just writing out the outermost ones here. Now, D, of course, is going to get 5 boxes because there's 5 different orbitals in 5 different arrangements. So this is what it looks like. Very paramagnetic. A lot of lone pairs. Okay, so we're going to become +3. Well, we're going to lose that electron, and we're going to lose, what, 2 more. All right? So what we're going to get is we're going to get argon. No more S, so no need to write it. And we write 3d what? We lost 1, and we're going to lose 2 more, so 3d3. Okay, and that would be the ground state configuration. The orbital diagram would look like, well, if you want to do it, you'd have an empty 4s. If you want to write the 4s would not have anything in it. And then you would need to put 3 electrons in our d orbitals. Okay, this is all 3d. And we'd write them something like this. If you put 2 in the back and left 2 open, it totally is acceptable. You need to write all of these electrons with the same spin. They seem to pair up and spin the same way. All right, so that's pretty straightforward. And not knowing if chromium did this or not wouldn't help. What you need to know, and very important, is we lose from what? From the 4s orbital first. That's key. All right, now you don't have to write this box if you want, but hey, it's there. Okay, so now we're getting back into which of these is paramagnetic. So we're talking about this. Which of these have a scenario where we're going to have multiple or at least one lone pair of electrons in an orbital? And that creates a magnetic field that can be affected, or at least be affected by a magnetic field. All right, so fluorine -1. Well, fluorine, as we wrote before, F -1 is equal to what? 1s2, 2s2, 2p5 if it's fluorine. -1 means we gain 1 more. Okay. Now zinc, and before we get there, let's talk about fluorine. If it's paramagnetic, we got to think that all of the orbitals are filled. So if I drew boxes, there would be no what? Orbitals that have lone pairs. So this one, or at least fluorine, is we'd say it's not paramagnetic, it's magnetic, or diamagnetic. So this one is not, because all of the orbitals are filled. What about the next one? Zinc +2. Well, we know zinc +2 is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 when it's what? An atom. It becomes +2 by, guess what? Losing from the 4s, so you get rid of that. If you notice, every single one of these orbitals are filled. So zinc is, again, diamagnetic. It is not paramagnetic. It doesn't have any lone pairs. How about titanium? If you're not aware of what titanium looks like, let's get there. So titanium is 4s2, 3d2. Let's go. So titanium is argon, 4s2, 3d2. Okay. So what do we know? Well, we know that argon, everything's filled. And we know that the S is filled, but the D. Now, some people might think, because they're not thinking about Hud's rule, oh, wait a minute, 2 Ds, that would mean 2 electrons would go together, and this is not paramagnetic. But you should know that you have the S, which has the 2 electrons, and then you're going to have the what? The 5 Ds. Sometimes it's really helpful to draw the orbital notation. The D's by what? Hud's rule would be in separate boxes. So this creates the scenario for paramagnetism. Remember, having spins that don't cancel out in electrons in empty orbitals have an effect, or at least are affected by a magnetic field. These electrons, their spins are canceled. Okay? Easy to make this mistake if you don't assume something called Hud's rule, as we talked about. Electrons in the same degenerate orbital occupying what? Occupying a different orbital, the same energy level, or a different orbital of the same sublevel. I can do this. Okay. All right, so this clearly has some lone pairs. Paramagnetism means that the chemical compound, whether it's an ion or an atom, has a lone pair of electrons where the electron spins are not canceled, and then therefore creating a magnetic field because of their spinning in the same direction. All right, 7.32. The ground state configuration of Neptunium is radon 7s2 5f4 6-1. So this is a classic little question here. Draw an energy diagram that shows how the 7s, 5f, and 16 orbitals are related. Use arrows representing the 7 electrons that occupy. So we're making an energy diagram. Okay. So an energy diagram would be basically here's my energy. And of course, out of the group, okay, let's look at 7s. Let's go look at Neptunium. They're telling me that it's radon, and then it becomes 7s2, 5f4, 61. Okay, now they're putting the 61 at the end, but initially 61 fills first. Don't get confused by that. All right, so what we do is we would put our 7s2 here, lowest energy. Then we'd have the 6d, 1. Of course, we know 6, or the D's, have 5 different orientations in space, and there's 61. And then we have the F's, and there is how many? 4 of them, but we draw the boxes, and F's have 7 different orientations in space, and you should draw them all in terms of the boxes. And we have what? 4 of them. By Hud's rule, they'll go in separate boxes. And there we go, and this is the 4F4. Okay, 7s2, and that's how that would look. All right, so that's my 7, 4, 5, 6, 7 electrons. Of course, this is a what? Paramagnetic element. All right. Determine the ground state configurations of molybdenum, iodine, and mercury plus. Use a shorthand notation. Let's go find molybdenum. Fun to say. So we're going to start with krypton, and then we go to molybdenum right here. 5s2, 3d what? 4, but just like chromium. Okay, we have some divergence, so we're going to fill it out. So 5s2, okay, 4d4 will become 5s1, okay, 4d5, just like chromium does. Okay, let's do it. So shorthand notated, I got my krypton, my nearest noble gas, then I have my 5s1, and then 4d5. We're going to fill that d and take one from the s because it's got enough protons to pull from the s to the d. Okay, many reasons we talked about. Let's go get iodine. So iodine here is going to be 5s2, 4d1, all the way to 4d what? 10, and then what? 5p5. So iodine, okay, we're going to get again krypton, its configuration, 5s2, 4d10, and then you can have 5p5. Like all halogens, okay, it has 7 valence electrons because of the p and the s. All right, let's go mercury plus 1, losing 1. So now we have xenon, right? Mercury's a little farther down, the configuration of xenon. Then we have 6s2, 5d1. Ooh, detour. Let's try to get this detour here. So we have xenon, 6s2, 5d1, 4. This kicks in the 4f, 4f14, back to 6. I'm sorry, I'm at 5d10. Okay, so essentially we have that there. So let's move forward. So mercury plus, remember we're losing an electron. I just did it with it being an atom, is going to be the configuration of xenon. All right, 6s2, 5d10, and then 4F14 if I write it this way. Some people would say 6S, we start the 5Ds and the 4F, and the Ds come after. It won't matter, okay? I'm just keeping the Ds together here. So if you say 5D1, then 4F14, and then 5D, I'm just going to kind of write it in together to show 10 electrons in the D. You can do this a couple different ways. But careful, it was mercury plus. I said 6s2 if it was an atom, but if it's mercury plus, I lose one, and I'm going to lose from my S. And that's why that one right there is 6s1. We're going to lose from our S. This is going to be, all of this right here is going to shield for the S to make that S be destabilized enough to lose an electron. And by the way, good times here, Hg2, two of these can bond together. Two of these Hg pluses can bond together and become Hg plus 2. This is a dimercury ion. And interesting enough, these 6s1s of one Ag plus can actually covalent bond with another Ag plus to make this ion. So two of these can actually form a covalent bond. Pretty cool, okay? So last little piece. So let's explain a couple of different things, and let's go on to A. And A is explain in terms of number of protons, the effective nuclear charge due to screening, and the size of the orbital. Those are the three major things. Why chlorine has a higher ionization energy than aluminum. So if you look in the periodic table, all right, chlorine is in the same N number, N equals 3. And of course, we have some electrons in the P here and the P here, and there's no screening in the same P. So it's all about Z. Chlorine has a higher proton number, so therefore it attracts electrons. There's no screening within the same P because the P electrons, of course, are in different orientations. So it's all about Z in this case. Chlorine has a higher Z, higher number of protons. Therefore, it holds on to electrons a little tighter. That's why it's a little smaller. So chlorine has a higher Z. Okay. B. Chlorine has a higher ionization energy than bromide. All right, let's go there. So now we're talking about chlorine has a higher ionization energy. It needs more energy to pull electron than bromide. Now, what do we know? Well, going down, the atom gets bigger. We know that the N number gets bigger. So now we're talking about a difference in N. We've got electrons that are in a different shell or a different energy level that are physically bigger and farther away. So it's easier to remove electrons from bromide because the N number is larger. Its electrons exist in a different orbital that's bigger. Therefore, easier to remove because basically the proximity of these electrons are what? Farther away because N indexes size. So this is about chlorine having a smaller N. Therefore, proximity-wise, these electrons for chlorine feel the nucleus more and therefore harder to remove. So chlorine has a lower N number, which means, again, harder to remove those electrons because they're closer to the nucleus. C. Okay, strontium is larger than magnesium, saying it has a bigger, nuclear radius. So strontium is bigger than magnesium. So let's go there. These are alkaline earth metals, as the chlorine and bromide were halogens, but strontium is bigger because it has a larger N number. The orbitals are bigger. Basically, strontium has a bigger N. Very simple. So strontium has a larger N. Okay, A, B, C, D. Chlorine negative is larger than K plus. Chlorine negative and K plus. This is special. These guys are isoelectric. What do we know by isoelectric? Same number of what? Electrons, different number of protons, and who dominates? The Z rule. So let's make sure we understand that. Chlorine negative and K plus. So chlorine negative and K plus. K loses an electron. Has the same configuration as argon. Chlorine gains an electron. So all of these both have what? 18 electrons. Potassium has 19. It loses an electron, its valence, to come on 18. And chlorine has 17 protons, 17 electrons, and it gains one. So who's going to be bigger? Or who's going to be smaller? Well, when you have the same number of electrons, isoelectric, the one with the greater number of protons will be smaller. Okay? So chlorine's going to, even though it gets bigger by gaining an electron, and potassium gets smaller by losing an electron, okay, potassium's going to be smaller overall than chlorine. Now remember, potassium starts very big and chlorine starts very small. So bottom line is, potassium with the same number of electrons has more protons, has a higher Z number, therefore pulls in its electrons even more. So in this case, chlorine is larger because chlorine negative has a smaller Z. For the same number of electrons, it's got less protons. Therefore, electrons feel the protons less, okay, and actually, okay, can move away from them a little bit. All right, so E is the last one. The first electron affinity, this is the energy change when we give an atom or an ion an electron. So oxygen, as we know, is 1s2, 2s2, 2p4. And if you give it an electron, energy is released because it has a great ability to absorb electrons. That's why they call it oxidation. Oxygen can gain electrons very easily, so it's very stable to gain electrons because it has a lot of what? Higher number Z. Now, the second electron affinity, that means when you have O negative, that would now be what? 1s2, 2s2, 2p5. This will now be positive to give an electron because the charge, okay, is now negative. So we have to answer why the first affinity is negative. Okay, why is it stable to give an electron to the 1s2, 2s2, 2p4 value? And the bottom line is, okay, O negative has a smaller ZEF, effective nuclear charge. There's a lot more screening for this electron to jump in here. Remember, this thing has more electrons than protons. So there's a higher ZEF for O negative. There's a lower effective nuclear charge. Okay, this electron, okay, is able to join this atom of oxygen because it feels, okay, the nucleus enough to be able to stay there and be stable. So we say is the effective nuclear charge, ZEF, is actually larger for this electron because it feels the nucleus. The effective nuclear charge here for the O negative is less because it feels the nucleus so less because of the electron-electron repulsions of these extra electrons. Therefore, all right, this is not a stable scenario to gain an electron to this. You would have to add energy, right? Things are stable, okay, in electron affinity when you can easily add an electron. Electrons are added when they feel the nucleus more. So what they feel is effective nuclear charge. Here, remember, O negative and O have the same number of protons, but different number of electrons. And having an extra electrons repels this electron so that it feels the nucleus less. Therefore, it's not easily put there. It doesn't want to stay there. You have to give it energy, and that's why it's positive. All right, hope that helped in some small, tall way.